Our next speaker is Kirk Bosma of the Woods Hole Group in Woods Hole, Massachusetts. He is a senior coastal engineer there, and he is the leader of their coastal sciences, engineering, and planning team, and he does a lot of work with climate change vulnerability assessments. Welcome, Kirk.
I'll be honest, the first thing that scared me when I came here today was I saw this Macintosh here. And as a numerical modeler and some of the stuff we do, I got a little nervous. But hopefully we'll proceed through this talk. Now, I'm an engineer. I'm a coastal engineer. So I'm going to give you a little bit different take, I hope, on this whole thing. And I do work with a lot of climate change scientists. And I do think we communicate well. So hopefully that is relayed throughout this talk. And Juliet did mention that there's a next session coming up on modeling. I encourage everybody to do that, but we are going to start to, as Jamie did a little bit, start to leak into numerical modeling here a little bit. So here are the things that I'm going to talk about. First, sea level rise and storm risk. What is the real risk? Okay. Correct. Engineers like a number, right? We like to design to the 100-year level or a certain elevation. So part of the issue is, how do we start to define what that design criteria, when you start projecting into the future with ranges, really need to be. And a lot of what we're starting to do from an engineering perspective is start to integrate that. And I'll tell you how we specifically are trying to do that. I will leave climate change, I will leave sea level rise causes to the experts. I'm not here to talk about that. I'll touch on it briefly, but that is something that I never try to talk about. I feel it's like a political subject I don't want to get involved with. The next thing is vulnerability assessment. So how do we determine what is vulnerable, right? And I'll apologize in advance. I'm going to pick on some maps. I'm going to pick on everybody's maps a little bit. All the maps are useful that are out there. They're all beneficial, but they all kind of serve a little bit different purpose. Jamie kind of hinted at that. FEMA's doing one thing, and the hurricane, surge risk is doing another thing. Climate change planning, when you start talking about investing actual money into adaptations and solutions, is kind of another whole thing, right? Which leads me to the final thing, which is preparedness planning and adaptations. What should the plan be? Right? What are we going to do? Right? I'm an engineer. I like to solve problems. That's how we're wired. My wife always complains to me because every time she wants to talk to me about a problem, she says, "You don't have to fix it." I'm always trying to fix everything. She just wants me to listen, right? So I don't listen. I say, "Well, how can I fix it?" Right? That's the engineer in me coming out. So we'll try to figure out what the plan should be going forward. All right, so real briefly, this is kind of the dumbed-down engineer's view on sea level rise, which is all I really want to talk about because precipitation, well, I'll touch on precipitation, heat, all those things are extremely important, but as a coastal engineer, I live in a world where I'm on the water, near the water. That's what I'm going to focus on. So sea level rise, simple terms, thermal expansion of the water. So the water heats up, the specific volume gets bigger, right? It gets bigger, it takes up more space, so the water level comes up. Okay, things melt, right? Glaciers are melting. Increased water input from land-based sources. So those two primary drivers, and the people who talked before me probably have way better description of that. Basically, is my simple way of saying that's why water is going up, all right? It just happens to be in the Northeast and Mid-Atlantic that we're higher than the global average, right? So the global average is somewhere around 1.47, 1.5 millimeters per year. If you look at the NOAA chart up there, you can see that they're all arrows going up. So we've got 1.75 millimeters to 6.05 millimeters per year. That's higher than the global average. Some more of the recent research on the circulation, the Atlantic Meridional Ocean Current, says that's also driving increases in the Northeast. We're going to have water pushed in different directions, so we're going to have higher water in the Northeast. And what else do I care about? Where do the people live? People live on the coast, all right? In the world, 80% of the population of the world lives within 60 miles of a coastline, all right? 3/4 of the major cities are coastal cities, right? In the US, 40% of the population in 2010 lived within 30 miles of a coast, and that's growing. So not only do most of the people live there? People are continuing to come there, right? So we have a growing population on the coast. So sea level rise is something that's going to affect more and more people. It's an important topic. All right, so this is a chart everybody's seen. Everybody's shown it, in the talks that I've seen today. And this is, the National Climate Assessment sea level rise projections, okay? So here's the existing tide data record, here's satellite altimetry, and then these are the projections going forward from low to intermediate high, and we all have stressed, wow, there's a wide range, right? So what are we going to do? How are we going to plan for that? That's true. When we start looking at scenarios, one thing I always try to look at is like, well, if I select the intermediate high level at 2100 and say that's a projection, that corresponds to about 2070 for the highest scenario, right? So when I start looking at scenarios into the future, I can kill two birds with one stone if I start looking at different water levels, okay? The other thing, and I don't have to explain this to this room, but I can tell you right now, in a vast majority of the talks I give on this topic to other engineers, most of them still don't believe in climate change and sea level rise, right? We designed to the 100-year storm, that's what we're designing to, right? So I pulled this out just because I find it is some way that I can try to express that, this is real, it is happening. Again, the tide gauge records, satellite altimetry. When we first started looking at projections going forward, climate change scientists, they undershot, right? The projections were actually lower than what actually occurred over that next time frame, right? So the actual data, which is what sometimes people can really buy into as opposed to projections, has gone faster than what they originally thought it was going to happen, right? So it's real, it's happening. And it's been somewhat of an effective tool of convincing some people that, this is real. All right, so let's talk about what the risks are, what are the processes, all right? This is a simulation from the Boston Harbor flood risk model, which you'll be hearing more about as I go through this talk. It's also, Steve Miller from Mass DOT is going to be talking about that tomorrow. It's a modeling effort that was put forth to assess the climate change vulnerabilities to the central artery system in Boston, okay? It's funded by Mass DOT and Federal Highway Administration. It's one of those collaborative efforts where we have universities involved, we have state and federal agencies involved, we have, oh gasp, a private consultant involved looking at this. So this is some model results. This is just looking at one of our synthetic hurricanes. Winds are included here, and then you have water surface elevations for increasing water level here. This is in NAVD 88. We'll get back to datums in a second. But what I really wanted to stress here is this chart over here. This is water level, mean high water in Boston today, 2010. The annual high in 2010. So we're around 4.5, and then we go up to about 6.5, 7. And then you have the 1% risk water level. As you'll come to find out, I don't use the term 100-year storm very much at all, and I'll get back to that in a second. But here's 2010, we're around 10. Okay, a couple quick things on this chart to notice. Sea level rise, this is the range, right? So this is the uncertainty involved, right? If you go from 2010 to 2050, you have this uncertainty in where your water level is going to be. Up to 2100, your uncertainty gets more, right? These are the projections. So a storm today, a 1% water level today storm is approximately equivalent to the next 90 or so years of sea level rise, right? So we're going to be living with the daily 100-year storm, so to speak, in about 90 years, okay? So, storms now are important, right? But sea level rise in itself isn't really the issue. It's sea level rise combined with the storm events that really start to push the envelope on a lot of our infrastructure and of a lot of the designs that we actually have out there, right? So storms, right? We're just going to keep a tally. Storms are important. Sea level rise is important. This is a similar plot to what Jamie showed in New York. This is actually in Boston, okay? This is Sandy in Boston. Again, the blue was predicted. Red was actually observed. You subtract the two, you get the actual surge in Boston, okay? And the thing that I'd point out here is Boston really got lucky with Sandy. just because of when the storm surge aligned with the tide, right? Tide storm surge in Boston, unlike in New York, was at, approaching a low tide. So the net water surface elevation was only 7.4 feet, which resulted in about something that you'd have a 30% chance of getting in a year, okay? So not dramatic. However, if the timing was a little different, say 5 hours before that, Sandy rolled through, and we aligned it with a high tide, then we were at something where we were at 9.4 feet. This is NAVD 88, net water surface elevation, and we're over, your 1% chance getting in a year, okay? Tides are important, right? So far we have storm surge, sea level rise, tides, right? The alignment of tides, especially in the Northeast, is key, right? In the Gulf Coast, it's not as big a concern. The hurricanes come in, they're primarily the driver of storm surge. It doesn't really matter what the tide level is. You're talking about a foot tide range. Here we've got, tide ranges of, 10, 12 feet, right? So when the storm comes through, the timing of it is critical, right? Then I threw this wave graphic in here, which is from the South Shore during Sandy. So even though Sandy's water level wasn't that high, waves still cause major issues, okay? So we have tides, we have storm surge, we have sea level rise, or tides, storm surge, sea level rise, waves, right? All starting to become factors here in how we're really going to assess our vulnerabilities of a system. All right, so let me talk about, well, where do we start to go to determine vulnerabilities, right? What's available, and this is kind of, if you're a planner or at a community scale, what can you start to look at? There's tons of information out there, right? Is it applicable for starting to plan for climate change and actually doing engineering adaptations? Well, these are the FEMA maps. I could go on about these for a long time, but I'm not going to. Essentially, as was already mentioned, these are, basically backward looking, right? They're trying to gauge what this 100-year storm is going to do. They only consider the 100-year storm event. It's a transect-based analysis, so it has some spatial limitations. And they have a big job to do, FEMA, right? They're doing the whole country, right? So for them to get into heavy detail is virtually impossible. And it also doesn't really use dynamic modeling, all right? It's a transect-based approach, backwards looking. And when we're talking about climate change and projecting forward, the last thing we want to do is kind of look back. Right? So what about these bathtub models like the Boston Harbor Association? And I can pick on this a little bit because I was involved with this project. So these are valuable as well. They serve a purpose. They're kind of the first order look, in my opinion, of where flooding may occur. Right? They're being used a lot right now. Again, they show kind of the flood depths, where water is going to be. I can't remember exactly what scenario I pulled, but it shows certain areas that would be flooded in the city. And they're based on this standard bathtub. Basically, you take your LiDAR data, you say your water level, you want your water level to be a certain elevation. Okay, what gets wet, right? It's a simple subtraction. But they don't really reflect the dynamic nature of flooding, right? We've already talked about waves and tides and all these things. None of those are in there. It's just a static water elevation that they overlay over the topography, right? So it doesn't account for any joint flooding conditions either, right? We have precipitation increasing intensity coming down the rivers. We'll talk about that. Oh, I just added another one, precipitation, right? It's changing, right? So you got to account for that. And usually it doesn't include, in these urban areas, dynamic effects of infrastructure. We have in Boston the Charles River Dam, the Amelia Earhart Dam. Those operate, they function, they do things, right? Those aren't in these models either, okay? So good first order look, but I'm not sure you want to use these results to do, multi-million-dollar solutions for your city if you're faced with that decision. Okay, so Jamie talked about the hurricane inundation maps. Now, here's what it is for Boston. They're based on different risk levels. I think this is a little bit different color scheme, but these serve a valuable purpose as well. They're the worst possible scenario, as I understand it, or the 10% scenario, right? It's the worst storm at mean high water. There's no associated risk planning involved. This basically serves the purpose of human life evacuation. That's what we need to use. Jamie showed some of the slosh results. They're coarse. They have to be run. It's a projected model. They have to predict. Like he said, they've got to be ready now. They don't have time to wait for for detailed results. So that's where that downscaling and resolution comes. But that creates some local inaccuracies in the modeling when we have very coarse grid spacing. When you start to talk about an individual building that you want to assess, this might not be the right tool to use. It's just hurricanes, right? Everybody knows up in the Northeast, hurricanes alone aren't what's causing the flooding up here. We have nor'easters that cause a big part of that. So again, they serve a purpose, but when you start talking about planning for the future, looking out forward, might not be the right tool. Again, all of these are valuable maps and valuable tools, but I don't think anyone's quite hit the nail on the head yet. All right, so then there's these hydrodynamic models. We'll be hearing about more of these later today, right? So I'm going to present one of those versions. You'll hear about others as well. They start to include all the relevant physical processes, you know, all those checklists that we started talking about: tides, storm surge, wind, waves, wave setup, increased river discharge, sea level rise, future climate scenarios, okay? That takes time and effort and high-powered models to do, but you can do it. They also cover large physical areas. These storms are big. They propagate up from, you know, the Gulf, from the mid-Atlantic. So you have to get the physical area right to represent the storm, all right? So here's my little pitch on why the current maps are not necessarily good enough, right? When you start talking about urban critical areas, right? This is Boston, okay? This is basically a bathtub approach, right? I just said, let's say I have a storm, a combined surge and sea level rise scenario that goes up to 12 feet. Okay, so that corresponds to maybe a big storm in 2070 type time frame, right? 12 feet NAVD 88. This yellow just basically shows the water surface elevation. Now I'm violating everything Jamie just told you about ways to, to accurately project graphics, but I think we'll still get the point across with this. It's just a test here. So 12 feet, this is where you're going to get wet in the system. This is just a flat water surface elevation at 12, right? It's a bathtub. We raised everything up to 12. What gets wet? Okay? And you can include connectivity if this, you know, there's hills here, it doesn't get over that. But that's what's showing there. All right. Now, if I change it to the dynamic model results for a storm that comes up with a peak surge of 12 feet, look how real different, look at how different we're talking about here, okay? This includes the Charles River Dam. It includes the pumps, how they pump around the dam. Wind is a huge factor here, right? When you have a hurricane coming in, this was just a comparison to a hurricane event. You've got a significant different flooding on the south shore than you do on the north shore. Okay, again, this is looking at water surface elevation. So you have completely different planning profile to look at when you have the dynamic results with the waves and everything else, winds involved, than you do with the bathtub approach. Okay, just another kind of cut of that. I took a slice down the dynamic results right here. And again, the bathtub approach would basically put everything at 12, right? We'll just put everything at 12, and that's where it floods. This is looking down on the south side of Boston. This is the water surface elevation profile. This gap right here is this island, which is relatively high. But you can see it dynamically, it's much higher than 12 on the south shore because the wind is pushing the water that way. You have wave effects. You have actual wave setup and breaking in here. All these things come into play when you start talking about planning, doing a design of something. All right, so why would I say we need such a sophisticated approach? Well, the risk is high, right? When we're talking about hospitals or central artery systems where your evacuation isn't even going to happen if the roadway isn't there to get out. You know, one vent building goes down in the central artery system and you can't keep the tunnel open, even if water isn't getting in the tunnel, okay? So there's all these important pieces to it that we have to understand. Solutions can also be really expensive, right? So you want to base it on the most accurate thing. And these dynamic models also start to answer other additional questions, right? Where's the flooding coming from, right? What's the pathway? What does it look like? You know, is the volume of water that's actually getting into that system, right? Because it's a time-varying model. How much water is getting into that area? What's the length and volume of flooding? And then a key thing is you can also start to test engineering adaptations, right? So I can run a model, I can see where the flooding occurs, and I can put an adaptation in, rerun it, and see what the results are going to be, right? Now, there's a lot of different modules and models out there. This is just the two we're using here for the Boston Harbor flood risk model. AdCirc is the hydrodynamic component, and then SWAN is the wave and wave setup component. We've also used, and you'll probably hear later today about FECOM and SWAVE. We've used that as well. It's another good model that can do some of this dynamic processing. This is just the particular model that we developed here and we've been using in other cases. All right, so now there's this other whole issue, right? I talked a little bit about, FEMA just kind of projects a 100-year storm event. I would say, what is a 100-year storm, right? As Jamie just mentioned, every hurricane has a different forward speed, different radius to maximum winds, different track lines, right? So you can't just run a storm and say, oh, here's your flooding, okay? So we've taken a fairly unique approach to this. We're working with Kerry Emanuel here at MIT. He uses all the different global climate change models and basically creates statistical sets of storm events, say for hurricanes as shown here, that would potentially influence the New England area, right? These are 5,000 plus number of storm events, okay? He also, based on the climate change model, basically can change the intensity of the storms as you go in the future. So when we say, look at models in 2100, we use a different storm set than we do in 2000. It's similar to what the National Weather Service is doing, and it's basically a Monte Carlo simulation. But as opposed to just kind of varying the track line in the medium, small size, we're actually using this synthetic, large, statistical, robust set of storms from Kerry Emanuel. What does that do? That rules out this ability to determine these joint probabilities, right? So basically, I have so many storms I can run, I can basically start to take that range of uncertainty and say, okay, here's my distribution of that range, and now I can start to give you risk profiles within a city. We've done a similar thing for nor'easters. So we have both hurricane sets and nor'easter sets that we run through the model. We run thousands of storm events. It takes significant computing power, but we're not under a pressure to have it done in 24 hours, right? We can take a little bit more time because we're planning for the future. Here's what the grid looks like as a starter. This is the regional grid. So remember I mentioned we have to start at kind of a large scale? Well, this is the large scale we start at. It's got all the Gulf of Mexico, North Atlantic Basin, and then we're talking about massive period. And it actually goes all the way up into Canada. And fairly coarse resolution in deeper waters, but then as you start to get into closer areas, we basically have an unstructured grid that can get finer and finer resolution. What does that mean? That essentially means when I get down to the urban areas, I can have something on the order of 5-meter resolution, 5 to 10-meter resolution that I'm using in certain areas. So I can start to look at individual areas, individual buildings, and of course, none of this could happen without LiDAR data and some of the other data we have, but it becomes a pretty detailed model at that level. And here's an example of that model in Boston. Again, I showed you a section from the Gulf Coast. This is looking at the city. Here's the financial district here. You can't really even see the underlying aerial because there's so many points where we're calculating data. Again, pretty high resolution model, okay? Just another view of that in the financial district at some of the spatial resolution. Again, we get down to about 5 meters or so in critical areas. And then here's what it looks like when you start to overlay what the ground elevations are, the topography in the system, right? Okay, so then we start running all these storms, this Monte Carlo approach, this huge statistical database of storm events. I jump back down to the Gulf Coast here because one thing I do want to mention is we absolutely insist the models are calibrated, right? So we just don't run the storm events. We have to run a storm event and make sure that a historical storm event closely matches the observed data that occurs. So this is Katrina that we ran down in Louisiana area. Again, the arrows indicate wind speed magnitude. Color bar here is water levels. So here's the hurricane coming up, Katrina. See the water levels. You see it actually, this illustrates kind of the high resolution of the model. Water is getting pushed up the Mississippi River here. And so we compare it to what was actually observed by tide gauges, high water marks, those type of things. We did the same thing in Boston for the 78 storm as well as Hurricane Bob. So we calibrate the model to actual observations, right? Before we run all the thousands and thousands of different storm events of nor'easters and hurricanes. Another example, down in Galveston, just one of the hurricanes that we ran through. And then let me try to give you a sneak preview of Boston here. Now, Boston is in the process of being completed, but this is just looking at, zoom into the area. This is one of the synthetic hurricanes. It's not final results yet, but again, the water surface elevation, and you can start to see where flooding occurs. You'll notice the Charles River starts to actually fill up with water. The dam is in here. This particular storm event does not overtop the dam, but you'll notice there's two areas, at least in this preliminary results, that do flank the dam from both the south and the north, right? We zoom in on that a little bit closer. You're going to see that from this area up here, water starts to flow in. From this area here, water bypasses the dam. The dam's functioning, the pumps are in the model, they're pumping water out, but so much water gets through there that it can't keep up, and the Charles River Basin starts to fill up. Key thing about this dynamic model is it's all in there, so the volume of water coming around is somewhat reasonably accurate, so you can know exactly what the water level is going to do back there, what the velocities are doing, all those type of things. All right, so what does this produce at the end of the day? It's a little bit different type of map, okay? And it's not pretty, and we're still working on this, but it basically gives you inundation risk, okay? So it's giving you a risk profile, a risk percentage, as opposed, that's what the Monte Carlo approach is going to do, as opposed to a water level or a depth. So I can go anywhere in this map, and this is Galveston, Texas, work that we have completely finished. This was work done for the EPA. And we can look at what the basically risk is. So this little island right here, this is in 2100 with sea level rise in a storm event, right? So sea level rise alone in Galveston is basically going to make this island wet every day. So 100% chance in 2100 that this is going to see water, okay? If I go to these green areas out here, I don't know, let's say a yellow area, it's like 2% risk. I can go to that specific location on the map and say, in 2100, I have a 2% chance that I'm going to have water there. Okay? We can also figure out what the depth is too. But as planners, this is a first important step. So if I had a hospital at a certain location, maybe I have no tolerance for risk, right? I say, the minute I have any water there, I've got to start thinking about planning and doing something, right? Maybe you do. Maybe it's not as critical. So I can wait till I get a 20% risk before I have issues. Well, you can start to use these flood risk maps to basically plan that out. They come as a function of time, right? So you can look at a map in 2050, you can look at a map at 2070, you can look at a map at 2100. You can start to plan when you need to do something. Key, right? Because that doesn't mean, what I'm not saying is we need to go out and build a seawall around Boston tomorrow, right? You got to look at when you need to do it too and plan for it. There's, Cameron talked about the ranges, right, and the uncertainties. Well, what I'm saying to you is we have some time, right? Because of that range and uncertainty means we can track what's going to happen. I don't know what the water level is going to be 2050 exactly. I've got a range, but maybe I'll know a little bit better in 2040. I can establish a threshold of when my risk becomes too much for me. So if I'm the central artery and I say, ooh, I can't have any water there, but it doesn't get wet until 2070, I can wait maybe till 2050, establish a trigger point, look at what my climate change, what my sea level rise is doing, and say, okay, my risk has become too much, now I need to do something. Maybe it goes slower than we think. Maybe it goes faster than we think. But you can use these maps to start to identify those things. All right. Now we're going to get really fancy here. See if I can do this. 0, right? I can stop now if you want, or I can go. But I'm about 5 minutes away. Let me show you how you use this tool real quick, and then I'll call it quits. So those detailed grids, you get points everywhere, right? So I can go into an area. This is Galveston results again, which were tied to an economic model. If Jim Newman's giving a talk in a couple days, and we tied this economic model to him. But you can go in here, and you can go to any point in the domain and click on the location, and this Macintosh is giving me fits. Right? So you can start to populate, and I can go anywhere in here, and I can click a data point and look at what my risk profile is, right? So at this particular year, and I think this is 2070, at this location, I'm dry. Not until there's a 10% risk that I get water of this level, right? So I can start to look at any location in the domain, right? If I take a quick look at what that really means. Everybody's familiar with the Galveston seawall, right? So I just extracted some points from a model. Again, we're looking at 2070 time frame. So sea level rise is included in there, all these dynamics. And I'm going to go look at a point, just seaward of the seawall, look at that point. All right, so, 100% of the time it's getting wet, right? Right? I get water every day there. It's the tides. I'm on the other side of the seawall. If I jump to the other side of the seawall and look at that, now I have a 0.05% chance of getting wet. The seawall is doing its job, okay? It's working. Now if I zoom over to the west, where there's no seawall anymore, and click at that same elevation point of the one we just looked at, I have a 50% risk, right? So now what I can do in the model is I say, okay, one of the things Galveston was considering is, well, what if we economically increase the seawall down to the west, right? I can put that in. I can run the Monte Carlo approach again, give you a new risk profile, and they can compare the costs of damages saved without the seawall, the cost of the seawall, damages saved with the seawall, and say, does that make a worthwhile project to do? Right? Okay. This is the last slide.
Okay.
So, just results in Boston. Something else that we can do with the model is look at where the flooding is, and then this is where the very danger comes in. So you can look around in the model and start to animate and look at flooding within the city. I have fact sheets available if people are more interested in this model, but that's essentially the tool that we're starting to use and apply. So with that, I'll stop, and I'm sorry I went a little long, but I'll turn it over to you. Thanks.
Okay, thanks very much.